Okay, so let's look at this circuit here. We're asked to compute the following for the load: P, Q, power factor, and reactive factor. So we have some impedance Z1 here, some impedance ZL here. And what's important to recognize here is that this load here, or I'm sorry, this Z1, I just put it as one box here. But really, if you want to think about it, this is some kind of resistor and capacitor in series. And similarly, this is some kind of resistor and inductor in series. Or it might just be an inductor that has a resistance of 1 ohm. Alright, so then let's go ahead and it says compute the following for the load: P, Q, power factor, and reactive factor. We're going to do this. We're going to do this by computing S. By computing the complex power. Because if I compute the complex power, I can just look at the answer and read off P and Q directly. So there's no actual additional work to do. I just can literally read P and Q from my answer. Now, we want to also remember here, and I'm doing this example because we haven't done any like this before. Notice here, the voltage is given in RMS. So I'll put it off to the side here. Remember how we had a formula here? We're not going to use S is equal to 1/2 V times I conjugate. We're not going to do that because we're given an effective voltage, which means we use S is equal to V effective. And since we're given a V effective to start with, we're automatically going to have I effective conjugate. Or we can write this as the magnitude of I effective conjugate times the impedance of my load. And how do I do that's just Ohm's law, the whole substitution with Ohm's law and everything. So we'll go ahead and do this computation here, and I'll maybe do it both ways here just to illustrate that you're going to get the same answer. So let's go ahead and go through this. Well, again, this one is an easy one here. We just have a single loop I can write to get the current I, and that's going to be the current I through everything because this is a series circuit. This is 60 at an angle of 0 degrees, so in rectangular form that's just 60, volt RMS, because it would be 0 for the imaginary part. And so my current is simply going to be 60 divided by 2 minus j plus 1 plus j5, which is equal to 60 divided by 3 plus j4. So if we do that computation, we get the following: 7.2 minus J 9.6 amps. And this is an RMS. Now let's go ahead and do it by this method first, computing my complex power. So if I compute my complex power, well, first I'd also need to know what the voltage is. Well, my voltage is going to be simply my current times my load. 7.2 minus J 9.6 times 1 plus J5. Which gets me 55.2 plus J 26.4 volts. And then we could do the complex power is equal to 55.2 plus J 26.4 times the conjugate, remember it's always the conjugate, 7.2 plus J 9.6. Okay, so let's do that computation, and if we do that, we get 144 plus J 720 volt amp. Now we could already answer part of the question here, but I said I wanted to do it the other way as well. So we have my current here as, and I maybe should emphasize this is still RMS value. I was equal to 7.2 minus J 9.6. Now if I convert this to polar, we get 12 at an angle of minus 53.13 degrees. Amp RMS. Okay, so now to use this formula here, my complex power is the magnitude of I effective squared times my load, which that's magnitude of I effective is just this 12 here. So this would be 12 squared times my load, which is 1.J5. So if we do that computation, we wind up with the exact same thing. 144 plus J 720. So two different ways you can compute it, both give us the same answer. So which way do you do it? Whichever one is the easiest to remember. Sometimes people just like using this one, the V effective times I effective conjugate, because we're always going to find a voltage and we're always going to find a current. So we'll find one of them, and we can always get the other one by either multiplying or dividing by the impedance, and then just simply going through it. That way they don't have to worry about like magnitude, and I even wrote it down here wrong, magnitude squared. I did it correctly here, but I wrote it down wrong there. So either method is fine. But now we have to finish our problem here, but we already have two of the answers here. We wanted to know what the average power dissipated by the load was. Well, that's just 144 watts. The reactive power dissipated by the load is just 720 VARs. And now we're wanting to know what the power factors are and the reactive factors. Well, what we do is we take 144 plus J720 and we convert to polar. So let's go ahead and do that. I'm going to just do that real quickly on my calculator. I don't have that in my notes for some reason. And I get here 734 0.26 at an angle of 78.7 degrees. Now, what's really important here is this here is my apparent power that's on the load. So the apparent power is 734.26, and again this would be volt amps. So my power factor is equal to 144 divided by 734.26. Which is 0.196. And the reactive factor is 720 over 734.26. Which is 0.981. So this is clearly indicating to us that in this particular load that we're looking at, we're not getting much of the apparent power being delivered to us as usable power. Now, one thing that's interesting to do here is if you do the power factor squared plus the reactive factor squared, you'll always get 1. And that actually just has to go to a trig identity with another definition, but it's an interesting thing here. But one other thing we should point out here is when we get things like this, they're often wanting to know whether they're leading or lagging. And in this case, because it's a positive, this means it's lagging as opposed to leading. And what do you mean by leading and lagging? Well, let's think of it in this way here. Let's go back to a graph. Of my cosine function. So this has a phase angle of 0 degrees. Now, this here corresponds to a positive angle. Specifically, the angle it corresponds to, this theta v minus theta I, is the inverse cosine of 0.196. And if you do that, it actually turns out that that's 78.7 degrees. So this is phase of 0 degrees. And so in other words, we have just cosine of omega t. But then our answer is basically kind of a cosine of, I know it's 2 omega t, but I'm just going to talk about the leading and lagging here. 78.7 degrees. But what does that mean here? This is a horizontal shift to the left. So in other words, I would have to shift this graph to the left, and I'd have something like this. And that's not necessarily 100%. In other words, it's lagging. It's lagging behind the original curve here. If it was leading would be where it would be over like this, because now it's leading the curve. So easiest way to know whether your power factor is lagging or leading is just looking at it as whether it's positive or negative. So if the power factor is positive, we're lagging. And if the power factor is negative, we're leading. Okay? So the next thing I want to talk to, kind of finish up our discussion on power, and we're going to do it in the next video, is going to be, okay, well, how do I deliver a load that would get me maximum average power? And we'll even maybe go back to this example to kind of illustrate this.